Okay, so hopefully these values do not scare you. Okay, these questions do not scare you. What is the value of sine 0? 0. Power over 6, sine power over 6 is 1/2, and then root 2 over 2, and then root 3 over 2, and then it's equal to 1. Now, if you need to make a mistake, now it's the best time. Just practice. Okay, I don't want you to go into Friday's quiz and say, what, we have to know this? Well, ever since we talked about these values, I've said that these stay with you forever, as long as you are still taking math. Okay, so there's no reason to turn away from these. Cosine 0, it's equal to 1. And then cosine of pi over 6, it's root 3 over 2. And then root 2 over 2. And then cosine of pi over 3, it's 1/2. And then you have cosine of pi over 2 being 0. So what I hope is that through this frequent and intensive recalling, repetitions, you create a strong memory, a pictorial, graphical memory in your head, so that you actually can see the values, not just say it, but you can actually see it. Tangent 0, it's 0. Tangent pi over 6 is 1 over root 3, or root 3 over 3. Tangent of pi over 4, it's 1. Tangent of pi over 3, it's root 3. And tangent of pi over 2 is, what's tangent of pi over 2? Undefined. Okay, I'm using red color because just to show a little bit different. All right, in the space below, would like you to do a couple of things. I would like you to sketch y over sine x and y equals to cosine x. Okay, hope you still remember I told you that you should always be ready to sketch these two graphs, and these two graphs will still be very, very much relevant. Okay, for these upcoming weeks. Okay, give you a couple minutes to sketch these two graphs. So where's the starting point for sine x? 0, 0. All right. And what's the period? 2 pi. Very good. And what's the amplitude for sine x? 1. Very good. So there's not much of a brain damage over the break. Okay. So I just want to make sure that your memory is still intact over the break. If not, then just try to revive it. And then for cosine x, where do we start? 0, 1. Okay, it starts at the peak. What's the period for cosine? Still 2 pi. Amplitude, it's also 1. So okay, and we will use these sketches or the idea of these graphs today. Okay, so pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so these are the stuff that we have been doing. for the past couple months. So now, I think I said it before, and I'm going to say it again. Now, we have a total of 6 trig functions. We have sine, cosine, tangent, and secant, cosecant, and cotangent. So we did the graphs for sine and cosine. And now it's the time to cover the remaining 4 graphs. And I saw somebody shaking heads already. Now, the bad news is that, yes, there are 4 more graphs you have to do. The good news is that they won't stay here for long. I would also confess that they are not something that would appear very often in the future, and they're not something that's very friendly. So I would just say, please just bear with me, okay? Just please bear with me so that we can get through this, okay? Now, and the reason why I went over these values with you is to make sure that you have some foundation. I don't want to just bombard you with new stuff. I want you to use some old stuff that you know, that you can recall, and then you can put it over here. For example, we're going to draw a tangent graph. So when x is 0, tangent 0 is what? Tangent 0 is 0. So you just answer the question on the paper, tangent 0 is 0. So if you know your unit circle values, that's going to be very helpful. And if you want to get to 1, what should the angle be if you want to get a y value of 1? Pi over 4. Okay. And when we say tangent of pi over 2, it's undefined. And how do we show undefined on a graph? We will need to use asymptote. And by the way, why is tangent pi over 2 undefined? 1 divided by 0, right? So if you use the unit circle, it's 1 divided by 0. So therefore you have undefined. So now, if we go backward and think about, what is tangent of negative pi over 4? Negative pi over 4, tangent of negative pi over 4. What quadrant would it be? Negative pi over 4, it's quadrant 4. So tangent would be negative. And reference angle, it's pi over 4, so it would be negative 1. And then tangent of negative pi over 2 will be undefined. So now how do we draw this graph? Now these 3 dots seems like they would draw a straight line, but no, they're not a straight line. So you would draw a graph that somewhat resembles a cubic function. It's not a cubic function, but it does look like one. So that's a tangent graph. Okay. So if you look at this, what is the period of a tangent graph? Okay, it's pi. So I'm gonna put a little star right there because for tangent, it's pi and not 2 pi, right? I don't wanna go into the argument that some of you would say, oh, I thought it's 2 pi. Nope, tangent, it's pi. And we will continue to, well, we will draw the whole graph. So we're gonna replicate this. So every pi units or every 4 squares, you will see an asymptote. Of course, this is the parent function without any transformation. And then you will just go ahead and replicate. Okay, and the value of 1 is to the right-hand side of the midpoint. And the value of -1 is to the left-hand side of the midpoint. Okay. And then we'll go ahead and draw the graph. Now, just make some effort to make it more like a curve. Okay. So just like what we did previously, last month, once we settle a graph, we just replicate it. Okay, and where are the vertical asymptotes? And we say, wow, vertical asymptotes are here, 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 and it keeps on going. Well, how are we gonna write it in such a way that we don't have to list them out, because it's forever. It's infinite amount of asymptotes. So we will write down pi over 2 plus k pi. And we say where k is an integer. So what we're saying here, it's yeah, so we have an asymptote at pi over 2. And after every single pi, you will see another asymptote, whether it's to the right-hand side or to the left-hand side. After every single pi units, you will see a vertical asymptote. All right, any questions so far? All right, so what's the domain? Well, we don't include the asymptotes, right? So those are the places where you have the asymptotes, and asymptotes, vertical asymptotes means undefined x values. So domain, in this case, we are not going to use interval notation, because that would be nuts. We would just say x will not equal to pi over 2 plus k pi. X does not equal to pi over 2 plus k pi. Can you write down the range? I think you can write down the range. What's the range? Interval notation would be -infinity to infinity. Okay. So it's a little bit tedious. And that's why I don't really, I'm not a fan of these tangent, cotangent, secant, cosecant graphs. Not a fan of these graphs at all. Okay. All right, now, what about cotangent? What's cotangent in relationship to tangent? It is the reciprocal, right? So now I want you to go ahead and write this down. The cotangent x is equal to 1 over tangent x. Now, and we have the tangent graph drawn, and I want you to make use of it. Why do we have vertical asymptotes here again? You cannot divide by 0, right? And now if you reciprocate the fraction, it becomes 0. So that means for every single part where you see a vertical asymptote for the tangent graph, it becomes a 0. Because it was 1 over 0, that makes it undefined, and you do the reciprocal of 1 over 0, that becomes 0 over 1. So every single point that you see a vertical asymptote above, then it translates to a 0 y value for cotangent x. And then when you see 0 for tangent x, you do the reciprocal and it becomes undefined. So for the x-intercepts for tangent x, that would become a vertical asymptote. Become a vertical asymptote for the cotangent x. And now we're very fortunate. These are nice values. They are 1 and -1. So we do the reciprocal of 1, which is still 1. So when you see 1, 1 over 1, it's 1. 1 over 1, it's 1. So what you see is that the y value of 1 positioned to the left-hand side of the midpoint. And 1 over -1 is -1. Okay. So you have something like this. So that's the cotangent graph. So now, after you started drawing these lines, so you may say, hey, it looks like a reflected tangent graph. Okay. I would say, yeah, it sure does look like a reflected tangent graph. Whether it's reflected horizontally or vertically, it does look like reflected one way or the other. Period, it's still pi. And the asymptote, it will be just k pi, because first it appears on the y-axis, and then it just keeps repeating itself after every pi units. All right, so a few questions here. Do you understand why we use the letter K in this case? Do you understand why we use the letter K? Okay, we use the letter K because we are lazy. We're lazy. Okay, we don't want to list out all these asymptotes, so we just say, hey, let's just do K pi. Okay, and what does K represent? K would be K is an integer, whether it could be positive or negative integer, but K is an integer. So that's how it describes this repetitive behavior of the asymptotes appearance. Okay, and I really want you to ask yourself the why question. Like, why do we have asymptote? Okay, well, 1 over 0 or anything over 0, it's undefined. That's the reason why we have asymptote. I hope we can use the tangent graph to explain the outlook, the appearance of the cotangent graph. Okay, so so the domain, it's going to be x is not equal to k pi, and the range should be from -infinity to infinity. All right, make sure you stop me if you have any question. All right, now let's take a look at example 1 down below. For example 1, we have 2 transformations right here. What does the plus pi over 4 mean? Shift to the left for pi over 4, and the 2 right here means stretched vertically. Okay, so so that's no vertical shift. What's the period in this case? It's still pi because the b value is equal to 1. Okay, so for sine and cosine graph, we have 2 pi over b. For tangent and cotangent, the period it's going to be pi over b. Okay, so right. So now we have a phase shift of pi over 4. So that means our midpoint is going to shift to the left pi over 4 units. And our asymptote would be shifted to the left for pi over 4 units. And since the period is pi, so we can draw the other vertical asymptote. So this is a unit of pi. Okay, the width of this first graph, it's going to be pi units. And then we have a vertical stretch of 2. So originally we will go ahead and plot the y value of 1, and now it becomes y value of 2. And we will go from y value of -1 to y value of -2. So for our tangent graph, the first one, it will look just like this. Okay, so take a moment to replicate. Okay, so as I said, yes, it's a bit tedious. Okay, so it won't stay here for long, I promise you. And this is also not something you will see a lot after this unit. Not a lot in calculus either. We'll still have a lot to do with sine graph and cosine graph, in particular cosine graph. We'll do some word problems next week, and we'll focus mostly on cosine graphs. Vertical asymptotes, in this case, it will be x equals to negative pi over 4. Oh, no, sorry, my bad. No. X equals to asymptote will be pi over 4 plus k pi. Okay. Domain would be x does not equal to pi over 4 plus k pi. Okay. Make sure you ask yourself frequently, why do we use the letter k? Why do we do it? What benefit does it offer? Range would be negative infinity to infinity. That's the range. Okay. All right, so breathe. And then now, next page. Now for the next page, we have secant x and cosecant x. What's secant x? 1 over cosine x. And what's cosecant? 1 over sine x. Okay, now, so what I would like you to do first is this. What I would like you to do first is this. For this one, hope you are using pencil for the graphing so far. Please use your pencil and you do the following task very, very lightly. Okay, like I want to draw the graph so light, so faint that only you can see it if you look it up closely. Other people would not be able to see it. What I want you to do, use your pencil very lightly, make a cosine x graph. Okay, for the whole graphing area. Make a cosine x graph for the top one. Make a sine x graph for the bottom one. Okay, give you a couple minutes to do it. All right, so let me go ahead and sketch mine. Okay, and a sine graph, it's, oops. All right, so I hope everyone will find this pretty easy to graph the sine graph and cosine graph. Now, I want to make sure that you understand this as a protocol. Whenever you see secant x and cosecant x, you would think about, like if you see secant x, you would think about cosine x. You would actually graph very lightly the cosine x graph. Because we're going to make use of this to make the secant x graph. Well, how? Well, first, understanding the fact that it's a reciprocal, right? The cosine x value, it's in the denominator. So if cosine x is equal to 0, what will be the value for secant x? Okay, it will be undefined. So therefore, whenever you see the x value or the y value being 0, or it hits the midpoint, that's where you see the vertical asymptote. Because 1/0, it's undefined. Again, understanding the why. Okay, I do not want you to memorize, and please do not memorize the location of the asymptotes. I want you to know the why. That's more sustainable. And then looking at some easy points, look at the peaks. The peaks would have the y value of 1, and it's the reciprocal, which is 1/1. So we say, oh, they share the same points over there at the y value of 1. So we can make these solid points. 1/1, it's 1. And 1/-1, it's -1. So we got these major points aligned, and they share the same points. And now here comes the very simple yet philosophical question. If the denominator, in this case, which is cosine x, if the denominator becomes smaller, what happens to the value of the entire fraction? Okay, if the value of the denominator becomes smaller, the value of the entire fraction will go up. This is the reason why secant graph would go up on both sides of the of both sides of this point right here. Okay, because cosine x gets smaller and gets closer to 0, so the entire fraction gets bigger. Okay. And on the flip side, for the bottom part, okay, if the denominator gets smaller or getting closer to 0, then the overall fraction becomes closer to infinity. Well, because there's a negative sign, so it becomes closer to it gets closer to negative infinity. So the dark part of the graph and the asymptotes would be the actual graph for secant x. And if you can draw the cosine x first, your secant x graph construction would be a lot easier. If not, actually, I don't know what to say about if not. I have never tried it yet. All right, now for this, what's considered a period? This is considered a period. So just like a regular typical cosine function, this is considered a period. Or let me move it here, like yeah, this one. Okay. Well, maybe this one's better. So and up, the graph on the upper part and the graph on the bottom part, they together will be considered as a period. So the period for the parent function would still remain at 2 pi. Where are the vertical asymptotes? They are located at pi over 2 plus k pi. Again, k is integer. Okay. The domain, it's x cannot be pi over 2 plus k pi. And the range would be, now, I'll let you write down the range. Let's see if you can write it down. It's not all real numbers. It's not negative infinity to infinity. What is the range for this case? The range is negative infinity to negative 1, bracket, union, 1 comma, infinity. All right. So for secant graph, that's nothing in the middle. Nothing. Okay. So that's why I want you to have a sharp contrast between the cosine graph and the secant graph. Okay, this cosine graph, make it very light so that nobody else can see it except you. And then you make the secant graph really, really dark. All right, now, so that's secant x. Using this knowledge, go ahead and construct the graph for cosecant x. Okay, draw the asymptotes, draw the asymptotes and the remaining parts of the graph. The period would stay at 2 pi. Okay. So using the knowledge that we had, so 1 over 0, it's undefined. So whenever you see 0 for the sine x, or whenever it hits the midpoint, that's the location of vertical asymptotes. So you can write down the asymptotes are at k pi. Okay. Again, k is an integer. And then once you get more comfortable with secant and cosecant graph, so once you have the sine graph and cosine graph constructed, you will then find the secant graph and cosecant graph very, very easy to finish. because you just drawing the points from the peak and the bottom, and then just draw the remaining parts. All right. So still using what we learned last semester into this case. We'll use it for quite a few weeks, 2 weeks. All right, domain, x is not equal to k pi, and the range is just like the previous one, -infinity to -1 inclusive, and then 1 to infinity. Okay, make sure you put a bracket next to the 1. All right, now let's look at the example 2 down below. Now this is a cosecant graph. Okay, now so what do we do when we see a cosecant graph with some transformation? So this is what you would do. Right next to it, go ahead and write this down. So cosecant, it's 1 over what? 1 over sine, right? So you would go ahead and write down sine of 2x plus 1. Sine of 2x plus 1, and just like earlier, very lightly, all right, go ahead, graph this one out. So the b value, it's 2, so that means the period is pi. So, and that's a vertical transformation of 1. All right, now I'm going to draw a couple patterns here, not the whole graph. I want you to see that this is what it's going to be like. And then your vertical asymptotes would be the places where it hits the midpoint. And for the actual graph, it'll be like this. All right, so and then it keeps on replicating itself. Vertical shift up 1. Asymptote will be in this case, the asymptote would be k pi over 2, because it appears every pi over 2 units. Okay. And domain, it's x cannot equal to k pi over 2. The range, it's -infinity all the way to 0, including 0. And then from 2 to infinity. Okay, so that's the transformed graph. So tomorrow we come back, we do more practices.